Okay, for this next one, we're dealing with the systic timer. So the first question here is, what value should you use for ST reload to get a systic interrupt every 70 milliseconds on the LPC 1768? So we're going to use the equation that we've used before, which is, that time, or t, the period, is equal to ST reload plus 1 over the frequency of the CPU, or CCLK, we could possibly mark it as. So that's our equation. We can solve for ST reload here, and so we're going to have ST reload is equal to T divided by, T multiplied by CPU frequency, and then minus 1 is what we're going to end up with there. And so that's what we're going to get as our value for ST reload. And we're going to put in our values that we have there, which are 70 times 10 to the negative third for milliseconds, right? So this is seconds. And then we multiply that by 100 times 10 to the sixth cycles per second, and then subtract 1 off of that value, and we should end up with ST reload is equal to 6,999,999. So that's just pushing the math through, and that seems to make sense to us. That is within the values that we can have. So we do need to think about the fact that ST reload's maximum value is, so max value is 2 to the 24 minus 1, because that's how many bits we have to use for ST reload. So that's from the manual / the notes. But we do have to keep in mind that that is the maximum value, but that comes out to like 16 million. So because that's larger than this, we're okay. So for this next part, we do need to consider that problem. Or we may need to consider that problem. So if we ran this on a newer microcontroller featuring a 500 megahertz Cortex M4 processor, how often would these interrupts occur? So we're going to go back to our original equation here, and we're going to say T is equal to, and we're just plugging in now the value that we got before for ST reload plus 1, and now we're using a 500 megahertz processor, which is 500 times 10 to the sixth cycles per second, and this is cycles on top there, and that's going to give us our time, which is going to come out to about 14 milliseconds. So if we have a 5 times faster processor than what we have on the LPC 1768, we should have a 5 times faster cycle here. And so that's what happens, is we have 70 divided by 5 gives us 14 milliseconds. So if we increase the clock speed, because that is what the system tick timer is based off of, it will decrease the period of our timer. For this last problem, I actually have a different solution than what's given on the website here. So if you assume that we have a similar configuration and control capabilities on the new microcontroller, how could you write your code to have 70 millisecond interrupts on both processors? And what this was looking for is the fact that there's this register called stcalib. So stcalib gives you a value that gets you 10 millisecond interrupts. And it's built that way because that's often a thing that operating systems want to do, is to have an interrupt every 10 milliseconds in order to sort of load balance code that's running on the processor, and give equal time share to everything that's running. So if we have a configuration register that gives us 10 millisecond interrupts, we can just divide that 70 milliseconds by 10 milliseconds. Implies that we want 7 interrupts at 10 milliseconds each, right? And so that means that what we would want to do is write our code, use a static local variable, and count 7 interrupts. And so that would be the plan, is to basically, configure the timer using stcalib. That stcalib should exist and give us a count that equals out to 10 milliseconds on both boards. And therefore, we could use that to count the 7 interrupts that we want. and give us a 70 millisecond timer on both of the boards. And that's again why this is sort of built this way, so that we can have this consistent timing no matter which board we're on.